So that's basically the subtopic that we are looking at. The objective, I have 3 objectives that towards the end of this presentation, we need to really investigate and analyze. We need to understand the Lenz law. That's very important. The second thing is we're going to investigate Fleming's right-hand rule, and we are going to use the right-hand. Remember, we also talked about Fleming's left-hand rule, and now it's the right-hand rule. So I'm going to try to explain as to when and where you're going to use the Fleming's right-hand rule. And we'll also try to identify and list applications of electromagnetic induction. So those are 3 objectives for the aim that I have for this presentation. Now, shall we move on?
Yes.
All right. Come with me to the next slide. Here I got the...
Guys, please mute yourself.
Sorry, guys, I got this.
Guys, enough.
Okay, stop talking and check this discussion question. I got this discussion question, yeah? Check this out. Now the question reads, a floating compass is placed next to a coil of wire. When there is no current flowing through the coil, the compass needle points due north, as it is given in the diagram that you can see. But when a current is flowing from X to Y, what happens is that in the coil, the magnitude or the magnetic field of the coil at the compass is equal in magnitude to the Earth's magnetic field at that point. The question is, which diagram below? We have 5 diagrams down here. As you can see, there are 5 of them down here. All this 5, which diagram it best represents the direction of the compass needle when a current is flowing from X to Y? Now in this question, guys, listen up. In this particular question, first of all, when current flows, what will happen to that coil? What is going to happen? Can somebody tell me? Ileana? Somebody talk to me. Somebody talk to me. Oh. Wallace, what is going to happen in here, especially in the coil, when current flows from X to Y? What is going to happen? What will happen to that coil? Coil is basically a solenoid now. What is going to happen to that?
It will light up.
Come on, someone talk to me. What will happen to that coil, the solenoid?
Who's 911?
It's Clyde.
Naomi.
It will be induced.
Okay, listen up. What's going to happen is that when current flows from X to Y through the solenoid, what happens is that that solenoid is going to become a temporary magnet. Do you understand that?
Yes, mister.
All right, very good. So that will become a temporary magnet, So if that becomes the temporary magnet, then it means that it will have a north pole and a south pole, right?
South pole.
Yes? So because of that, this
Yes.
needle here, we have geographical north pole and the magnetic north pole, remember?
Yes.
Yeah.
All right. The compass actually points towards the North Pole, geographical North Pole, which is in fact, we discussed earlier on that magnetically it is the South Pole, remember?
Mm-hmm.
Yes.
And so the needle, the not thinking a needle is attracted towards the South Pole. So this needle will deflect to where the South Pole is, where the South Pole is. So after identifying the current direction, we are going to use right hand grip rule. Are you listening?
Yes.
Yes.
We're going to use right hand grip rule to identify the polarities of this solenoid. After identifying the polarity, the needle will point towards the north. Pardon, it will point towards the south because it's the north. It has this north pole property, and it is attracted to the south pole geographically. It is the north end. Is that clear, guys?
Yes, Mr.
All right, that's perfect. Let's now identify the current direction. So as current flows, I am going to insert the arrows on the coil to show you the current direction. And using the current direction, it's going to help us to identify the north pole using right hand grip rule.
Right hand grip rule.
So current is flowing this way.
Left hand is left hand is this one.
Are you listening?
Yeah, blow.
Yes.
Current is coming up this way, and it's coming down this way.
Okay.
Little.
It's going on, back up. Plus, follow this red ink here. Follow this red ink.
Boy, mute yourself.
Current going up that way, coming down this way. It's going back up on the inside, and it's coming down this way again. Going back up again, coming down this way, coming down this way, coming down this way. Are you following?
Yeah.
Yes, sir.
All right.
Yes.
So this is the current direction. I'm going to insert the arrow.
Yeah.
Oh, yes, sir.
Now you tell me, use your right hand grip rule. You got the arrows indicated on the diagram. Use your right hand grip rule to tell me which side, X is the north pole or the south pole. Tell me.
Not. So not to south.
South.
What is it?
South.
South. South.
South. X is south.
X is south pole, right?
Yeah.
Use your right hand grip rule and you will notice that X is the south pole. So
South pole.
this is the south end. If that's the south end, that means that this is the north pole, right?
Yes.
Yes.
Are you
Mr.
sure- are you
It's
sure
okay.
about that?
Oh.
So which end do you think which one is the one that you think the needle will point towards?
D.
All right, guys, let me have this again up for you. Let me do this. Current is coming this way. It's going out that way. And remember, this is the front end. If it is, this is a coil. This is a coil. Plus, you hear me?
Yes.
Yes,
Hear me?
Mr.
Yes, okay. Look at this one. It's a coil. This is how it should look. Look at the red ink that I have actually inserted on top of the coil. If I am going to...
If I forget you. If I forget you. If I forget you. If I forget you.
Mute yourself, yeah.
Hey, mute yourselves.
Ileana.
Mute yourself.
Ileana.
All right. I am going to insert the current direction, follow. It's going on. Can you see that?
Yes.
Yes.
Yes? Okay. I would like you to look at this diagram closely and tell me the North Pole and the South Pole.
Mr. X is the south, North Pole.
X is the?
North Pole. I don't know, I'm just saying. Yeah.
Yeah, not. Yeah, not.
Do you understand that? Class, talk to me. Do you understand that?
Yes.
Yes.
Yes?
No, Mister. I don't understand.
Okay. So
No,
here.
Mr. No.
No? Okay.
Use the
look at-
right-hand grip rule.
you can spend some time on this and you try to figure this out. But what I'm giving you is the correct. Who was that? Was that Wallace? Did you say that?
Right, Mister.
Okay, this is the North Pole and this is the South Pole.
I don't know if I'm correct, but yeah.
Well, it's right.
No, me is here.
So with that, class, with that, can you tell me which direction should the needle point towards? Remember, the needle will always, geographically, it is attracted to the North Pole, which is in fact, magnetically, it is the South Pole. So the needle will
South
point
Pole.
to the South Pole. And which one is that?
B.
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 Yes.
Are you sure about that?
Oh no, Mr. I think
D. D.
What is that?
D. Mr. D.
D. Yeah,
I don't know.
D. It will.
You guys stop
deflect this
guessing
way.
at this.
The needle will deflect this way. Can you see that?
Yes.
It will deflect this way. Now, since the North Pole is somewhere here, the needle will actually untwist. The answer falls between C and D, but D is the correct answer. Now, this question is taking some time. Let's move a little bit further down.
Yes.
Yep. So here we go. Now, Lenz law. Why we are talking about the right hand grip rule? Because this right hand grip rule is going to help us to understand when we're dealing with Lenz law. Right hand grip is very much important. It's equally important. So we need to understand the discussion question above to further understand the concept of Lenz law. Now, Lenz law again, it states that that an induced current always flows in such a direction so as to oppose the change, or it opposes the motion causing the induced current. Now, Lenz law is well used to determine the current direction in a solenoid. Now, Lenz law, it goes well with the solenoid, the concept of solenoid, current induced in a solenoid. So let's take a look at this idea here. Okay, I'm gonna explain Lenz law, what it means by the current flow of current that opposes the motion causing it. I'm going to explain that with a few diagrams underneath. So I'm going to do that in just a while. But let's take a look at Lenz law as a form of conservation of energy. Remember, conservation of energy is neither created nor destroyed, but it simply changes form from one to another. So when the magnet is moved towards, now let's take a look at this diagram closely. This diagram. I'm going to explain this. When the magnet is moved towards the solenoid, current is induced in the solenoid. Why does this occur? Well, when this magnet here, when the magnet is moved to the right, or it is brought closer to point P. When it's brought closer to point P, current is induced, or current is basically flowing through this whole segment here, this solenoid. Why does this occur? Well, electrical energy cannot be created without any form of work being done. So electrical energy is a form of energy, and work we discussed last year, that work is when energy transfers from one form into another, we say work is done as well. And so this kinetic energy, movement done with the magnet, once when it is brought towards the solenoid, force is applied, distance is covered. So work is given by force times distance. Work is done. So the work done by moving the magnet towards the solenoid, point P, basically we're saying that the work done is then converted into electrical energy. So it induces current somewhere here at point P. But the definition of Lenz law, the concept or the law, Lenz law still remains that the current flows in such a way to oppose the motion causing it. So the motion is, the magnet is brought towards the end P. North pole is brought closer, make note of that, North pole. But when North pole is brought closer, current flows in such a way to oppose it. Now what happens, what does that mean? It means that we are going to use our right hand grip. We're going to use right hand grip. So the North pole is brought closer in order for some repulsion or repulsive force to take place. What should this end be? End P. What should that be? Somebody talk to me.
Mr. What did you ask again?
My question is, when North pole is brought closer, when current passes through the solenoid is going to become a temporary magnet. So which means that if it becomes a temporary magnet, then it will have those polarities, the North pole and the South pole. Now, which two poles attract each other and which two poles they repel each other? Let me put it this way. Like poles, do they attract or repel?
Repel.
They repel each other. Unlike poles, they
Attract.
So the North pole is brought closer. North pole is brought to point P. So in order for the solenoid to become a temporary magnet, to push this one away, what should point P be? Will it be a North pole or a South pole?
It will become a North pole to oppose the change in motion.
Exactly. So it will have to become a North pole. So every time when North pole is brought closer, this has to be North pole to push the magnet away. Is that clear?
Yes, Mr.
Yes, Mr.
All right. So with that now, we can be able to identify the current direction. How? How are we going to identify current direction in here?
Right hand, Fleming's right hand.
Yes, we're using right hand grip rule to do that. So using right hand grip rule, remember thumb will always point towards the North pole. So have your thumb pointing towards the North pole. This time, this temporary magnet, your thumb should point towards point P. With that now, you are given the current direction. The current direction is indicated there. Can you see that?
Yes.
All right, that is the first part. When the North pole is brought closer, then this end has to be the North pole to push it away. That will help you to identify the current direction using right hand grip. This time the North pole is being pulled away. The second case here, North pole is pulled away. Once North pole is pulled away, then this end needs to, or this end has to tend to South pole to attract. Pull back the North pole. Remember?
Yes, Mr.
Unlike poles, they're gonna attract each other. So this will have to somehow change it to the South pole. That means that this becomes a North pole. Using your right hand grip rule again, you can be able to identify the current direction as it is already given on the diagram. Is that clear? Do you understand this Lenz law?
Yes.
Yes, Mr.
Okay. That's some yes. Just some of you hesitate a little bit. Let's go a little bit further down. Now, when the magnet is moved away from that is the same thing that we are talking about. This is done. And when magnet is moved towards or away from a solenoid, work must be done to overcome the opposing force. So we are saying that work is done. So the work done is converted into electrical energy, which creates the induced current. Now let's move a little bit further down to the next here I got these examples here, just to identify or understand, just to understand Lenz law. Let's take a look at these examples. The first example here, A. I got a solenoid, and we are going to identify the current direction together. So this time, tell me, North Pole, is the North Pole brought closer, or it's moved away from the solenoid?
Away.
It is moved away. You see this? It is the North Pole is moved away. When the North Pole is moved away, what shall this, let's say, add? What shall I label that?
South.
No.
It should be south to attract the North Pole.
Exactly. So it has to be the South Pole. When it is moving away, this has to be the South Pole to pull the magnet back in again. Clear?
Oh.
Yes, Mr.
All right, so that means that this is the North Pole. So use your right hand grip rule and let's identify the current direction together. I am going to write it on, I'm going to indicate it. You tell me if it is correct or wrong, okay? Current direction, is that correct?
Yes.
Yes.
No.
No, Mr.
Oh my God.
That
Yes.
is wrong, that is wrong. Current
No,
direction,
it's going down.
current direction is, coming down.
Yes.
It's going to be like that, yes?
Yeah.
Yes, Mr.
This is Lenz law. Now let's take a look at B and try to understand it. This time North Pole is brought closer. North Pole is brought towards this end here. Let's say this an X. What shall X be?
It should be north to oppose
North.
the motion.
Very good. This is the North Pole now. This is the North Pole. So how shall you identify your current direction? Current direction is this way.
Going up.
Yes.
Yes.
Is this clear?
Yes, Mr.
All right, let's take a look at the next one. C. This time it's not the North Pole, but it's the South Pole. Okay? It's the South Pole. Now, South Pole is brought towards the towards this end, X here. What will that be?
South.
Yes?
Should be south.
South.
That's
South.
to be south to push the magnet away again. Can you see that?
Yes.
Yes.
So current direction again,
Should be up.
like that, huh?
Yes, Mr.
Okay, and finally,
Yes.
it's the opposite. So when it is moved away, South Pole is it's being pulled away from the solenoid. So current direction, that means that this will have to be the North Pole to attract it.
North.
This is becoming the South Pole, so current direction will be
Going
They
up.
move down.
Oh,
Down.
down. Down. Okay, Wallace.
Now, do you understand Lenz law now?
Yes, Mr.
Yes.
Very good.
Yes.
Yes, Mr.
I'm grateful for that. Okay. Now let's move a little bit further down. Okay. But time's up, right?
Yeah, Mr.
Yeah, Mr.
When are we coming back?
It's 11 o'clock.
When are we coming
15
back?
minutes.
15